So in this problem, in his battle with Goliath, David twirls a 0.5 kilogram rock on a 2-meter tether with an angular velocity of 2 revolutions per second. What is the centripetal force on the rock? Well, we've already said this centripetal force is the mass times the centripetal acceleration. That's the force required to keep this thing moving in a circle. Again, if it's going to accelerate at a sub c, then the force acting on it has to be the mass times that acceleration. That's what Newton's second law says. Notice we're not saying what's supplying it. Excuse me, in this case, right, David has a little pocket here that's attached to some strings, and he holds them like this. And so it's the pouch that's supplying the centripetal force. So you might call it a normal force or something like that, pushing that way on the rock. But all we're calling it is a centripetal force because it's the thing that's making it move in a circle. That's equal to ma sub c, which is equal to m v squared over r, or equal to m omega squared r. Right? Omega is 2 revolutions per second, but but I can convert that into radians per second, which is what I want to do to be in SI units. And so I want to multiply that by 2 pi radians per revolution, which gives me an omega, which is 4 pi radians per second. And now I can evaluate this. I can say, well, the mass is 0.5 kilograms times 4 pi radians per second squared times 2 meters. I get about 157 newtons. Comes out as kilogram meters per second squared. Notice the radians, I can just drop them because they have no dimension. So in this problem, we're to calculate the centripetal force on a 900 kilogram car, making a curve of radius 500 meters at 25 meters per second. And so maybe I'll just use this. And I'll do this. And how do I do that? I'll just draw a circle inside. So here's my car, say. It's on the road. It's going this way at 25 meters per second. Can we all agree that if the road was icy, it would just keep going straight as it's going around this curve, right? It's got to be accelerated this way. A sub c is equal to v squared over r, and that's equal to 25 meters per second squared over 500 meters, which is 1.25 meters per second squared, right? And so the force, the centripetal force, is equal to the mass times the centripetal acceleration, which is 900 kilograms times 1.25 meters per second squared, which is 1125 newtons. And so that's the force that's being exerted in this direction. Question B says the following. So the question is, if the force that we're talking about there is due to static friction, which it is, remember when I said if it's slippery, what would the car do? If it's slippery, the car can't get, the force can't work. And so it's friction that's causing the car to go around the curve. And not only that, it's static friction, because like we were talking about before, when a wheel is rolling, if a wheel is turning this way, the part of the wheel that's touching the road is at rest with respect to the road. And you may have to experiment with that, but as a wheel rolls, the part that's touching the ground is not sliding. It's stationary with respect to the ground. And so to answer this question, first I'm going to write down these numbers. A sub c is 1.25 meters per second squared. M is 900 kilograms. F sub c is 1125 newtons. The radius is 500 meters. And V was 25 meters per second. And this is our car. But now I'm going to draw the picture a little differently. I'm going to pretend we're looking from this direction. And so we're looking at the car's coming towards us, right, but we're looking at it this way. And so I'm going to redraw this. And here's the car coming at you. Here's the road. I'm going to try to draw it flat. Here's the road. Here's the car. There's a person driving the car. There's a steering wheel, like that. And so now the car is coming at you. And here's the center of the circle over here. And so this distance is 500 meters. And again, the acceleration this way is a sub c is v squared divided by r. And we already said this 1.25 meters per second squared. And what are the forces on this? Well, there's this F sub c, which is really a static friction force, right? We're just giving it the generic name of the force that makes it go in a circle, but it's a static friction force. There's a normal force, there's a gravitational force this way, which is mg, and there's a normal force this way, which is Fn. And so if we wanted to break this problem down, we're going to say, well, the car is accelerating this way. If I turn this into a free body diagram, I have a normal force, I have a static friction force, I have a force of gravity, I have an acceleration this way, and I draw my coordinate system like that because I want one of the axes of my coordinate system to be in the direction of the acceleration. I'm going to erase part of this, and I'm going to say, oh, I'll erase all of it. Since I've got my free body diagram, I'll just erase that, right? And now I can just say, look, sum of the forces in the x direction equals ma sub x. That's equal to ma sub c, which is equal to mv squared over r. And then the forces are just the static friction force. Right? If you remember from the definition of the static friction force, it's less than or equal to mu sub s times the normal force. But this is saying, what's the minimum value of mu sub s that will allow this thing to work? And so that means that mu sub s is going to be small enough so that these two are equal. If it got any smaller, this wouldn't be able to make the car go in a circle. And so that means that F sub s is equal to mu sub s times the normal force. And so now we get mu sub s times the normal force is equal to mv squared over r. And so mu sub s is equal to mv squared over r times the normal force. They're asking us what the value of this is. Well, we know what m, and we know what v squared, and we know r, but we don't know the normal force. So we have to go back to the sum of the forces in the y direction. equals ma sub y, and that's equal to, what are the sum of the forces in the y direction? Can you pause that and tell me? It's 0. And so that means the normal force minus the force of gravity equals 0, or the normal force is equal to the force of gravity, and that's equal to mg. And that means that mu sub s is equal to mv squared over r mg. The m's cancel, and it's just v squared over r times g. But what is that? That's 25 meters per second squared over 500 meters times 10 meters per second squared, and that comes out to 0.125. That's not a very big coefficient of friction, and so a typical road is going to have a coefficient of friction of maybe 0.7 or something like that. And so you'll be able to stay on the road, even on a wet road, which is what you want to be able to do. And so if the speed limit is what it was on this road, 25 meters per second, which is about 55 miles per hour, going around this curve, you should be fine, even if the road is a little messy. So we're going to do a car going around a curve again. And so I'm going to have, again, I'm going to have a radius r, and I'm going to have a car going around this curve, and its speed is v, right? And the mass of the car is m, which we may or may not need. Except this time, instead of being a flat road with friction, the road is banked. You may have noticed that often roads, especially highways, get banked as they go around a curve. And so we want to determine theta in terms of r and v and anything else, so that the car will make it around this curve without sliding off the road, even though the road is frictionless. And so once again, I'm going to have an acceleration this way, a sub c, which is v squared over r. Right, and that tells me that my centripetal force is mv squared over r. And just like in the previous problem, I'm going to draw the car looking at me. Right, and so here is the tilt in my road, and here's my car. Right, and he's got a headlight and a headlight, and a wheel and a wheel. And then he's got a driver here, and there's a steering wheel, smiling, and so on, right? And so here's my road, and here's the angle theta. Try that again. That's the angle theta, right? And I'm going to identify some forces acting on my car. And so the force of gravity is equal to mg. That's going this way. And then the normal force is perpendicular to the road, and that's going this way. The centripetal acceleration, a sub c, is going that way, right? And those are the only forces. I don't have a friction force or anything like that. And so when I draw a free body diagram, before we rotated our coordinate system for a tilted slope, but here our coordinate system is going to look like this if this were a free body diagram, because I want one axis along the acceleration. The acceleration is towards the center of the circle, which isn't down the slope, but towards the middle of the circle that the road is doing. And so if I were to actually draw a free body diagram here, I'd have my normal force going this way, I'd have my acceleration going this way, a sub c equals v squared over r, I'd have my force of gravity going this way, force of gravity equals mg, and I do my little coordinate system like that. And then I would take my marker and I would draw the coordinate system on here. And then I would indicate where my road was. So this is where this is the tilt of the road, and that means this angle here is theta. right? Because that's the tilt in my road. And this guy is not on my coordinate system, and so I've got to write components for this guy. And since my coordinate system looks like this, I'm going to say this angle here is 90 degrees minus theta, and that means this angle here is theta, because this is a 90-degree angle, the normal force in the surface, and all three of these angles, this one, and this one have to add up to 180. That means these two guys have to add up to 90, which means this guy's got to be theta if that's 90 minus theta. Anyway, you can work that out on your own. And now I can draw the components of this force. I've got a y component going this way. That's F and y. And I've got an x component going this way. That's F and x. And you can see that F and x is equal to F and sine theta, and F and y is equal to F and cosine theta. Is that still on the screen? It looks like it is. And so I'm going to have to come over here and draw. So let's redraw the free body diagram over here. And I have the y component of the normal force going this way. I have the x component of the normal force going this way. Maybe I drew it a little long, but okay. I have the force of gravity going this way. I have the acceleration going this way, which is v squared over r. Right? I have a coordinate system that looks like this. And that's my free body diagram, right? And so it's the x component of the normal force that pushes the car around the track, that provides the centripetal force. I could say F sub c is the x component of the normal force, right? Which is Fn times the sine of theta, right? And so Fn sine of theta is equal to, well, let me just back up a second and write sum of the forces in the x direction equals ma sub x. That's equal to ma sub c. That's equal to mv squared over r, right? And those forces are just Fnx, so it's Fnx, which is equal to Fn sine theta is equal to mv squared over r. And so I have a relationship between theta and v squared and r and m, but I've got this Fn in there, and so I've got to sort of work that out somehow. This leaves me with Fn sine theta is equal to mv squared over r, but I can use my sum of the forces in the y direction equals ma sub y. That's the acceleration up and down. That's equal to 0, and so that says Fny minus mg equals 0, or Fn cosine theta is equal to mg, or Fn is equal to mg over cosine theta. And now I can take this piece here, which is equal to the normal force, and I can stick it in there, right? Because what I'm looking for is a relationship between theta and m and r. And so I just plugged in, and I knew it was going to come out of here somehow, and I'm just trying to solve. And so now I can write mg over cosine theta. That's this piece. So I'm rewriting this equation here, except instead of putting my normal force here, I'm putting this there, because that's what the normal force is equal to, times sine of theta is equal to m v squared over r. There are a few things that happen. The masses go away, as they often do, right? And I get g times sine theta over cosine theta is equal to v squared over r. If I want to have this thetas on one side, I get sine theta over cosine theta is equal to v squared over rg. We saw this equation before. Sine over cosine, if you remember, is tangent. Tan theta is equal to v squared over rg. So I could say theta is equal to the inverse tangent of v squared over rg. Make a little better squared there. Right? And if I want to come all the way over to here, I could say, in the kind of problems we've been looking at, like in the last problem, I said, well, v is 25 meters per second, and r is 500 meters. That means that theta is equal to tan inverse of 25 meters per second squared over 500 meters times 10 meters per second squared. I get about 7.1 degrees. So when the road is tilted at this angle, a car going at 25 meters per second will make it all the way around the curve without sliding off. Now, you can't have a road, you can't have people go at exactly some speed, but if you tilt the road for some average speed, then even a little bit of friction will make the correction for cars that aren't quite going at that speed and still keep them on the road.